I'm really honored and excited to be here, and it's a really good time to be here actually, because I am at the end of my 5th year, starting my 6th year. I'm going through the tenure process right now, so I had to put together the whole dossier, the whole 43 pages of everything that I've done, and I will say that the department level, I already passed that level, but we gotta wait for the rest to see how it goes. But it's a good time to reflect, and so doing this talk is really fun for me to come back. I feel like I'm coming back and kind of giving honor to the program that really helped position me to be doing what I'm doing right now. So I did have some background slides, but I'll just blow past those because Panos covered that. So yeah, I did a bachelor's and master's at RPI. And this is where I started to dare to be different, is getting this PhD in design science here at University of Michigan. This is me on graduation day with my mom, Rich and Panos, 2010. And did a postdoc at Iowa State for a year and interviewed, and then Purdue, I got this phone call from the department head. And he said after the interview, "Are you still interested in Purdue? We want to have you here." And I said, "Yes, I am." He provided some other information. And then I was like, can I even be a professor? Major imposter syndrome. Can I even do this? I don't know if Panos remembers me calling, like, "Panos, did you convince them to hire me or something?" And he said, "I didn't do anything. I was like, can I even do this? Can you imagine? You come from a lab with like a Panos, and it's like, I'm about to start this whole R1 thing. You know, all those buzzwords, the R1 institution and research and all of that. And I'm like, can I even do this? Literally, this is how I was when I took the position. And I finally figured out, oh yeah, actually I can do this thing, and I could do it pretty well. I mean, after I got into it. One of the things I wanted to point out are just some major contributions that design science has given to me. And what's nice is that it creates a space for you to have free and creative thought. And the wild ideas are welcome. And so ME 555, I have a number right? Design optimism. That was a seed of an idea started in that class, and I'll talk about how that seed has become like a tree almost since that time. Had I not been in a space like this, I think my thinking would have been very confined. I'd have been very shy about my ideas, but in this environment, I was free to express them. Also gave me some ideas on how to pick students. I had no idea what I was doing as a professor. I mean, go back, can I do this? Where do I begin? I begin with what I saw, and so I picked students a particular way, and I was very intentional about how I picked them and what they were working on, and really positioned me well for interdisciplinary studies. Lots of collaborations, and I feel like I'm what I call build bridges. I'm the one that's sitting on teams where it is like a very traditional engineer. There may be someone from psychology, and I'm able to really engage and help bridge the conversations a lot better. And I had an epiphany when I was working on a center grant for AFOSR. It was a team, it's myself, there's a clinical psychologist on it, there's the PIs from University of New Mexico in electrical engineering, there's a computer scientist on the team as well. And we were writing up the proposal, and I was like, this thing is on human-machine teaming, and I'm looking at the lit review, I'm like, there is like no paragraph on the teaming part. No one saw it, no one noticed it, so I got into the literature and wrote that up. And they were like, oh my gosh, thank you, Tahira. We have a whole grant on teaming, and there's no literature on it. And I just said, I'm like that bridge person. I really could just get my mind into other disciplines, get what I need out, and so I just saw that, and I was like, I guess that's also my role. I just kind of fill those gaps as well. So those are some things just on a high level that has really been influential in my career so far. And so talking about the students, because of how I selected them, I didn't know that it was a big deal that when you go up for tenure, you should have one student graduate or be close to having one. I have 3 that went out. So these are all 3. This is Joran, Yui, and Wanlin, who will start in like a few weeks at Stanford. So I got 3 out by the time they started reviewing my packet. Okay. So yeah, I'm a professor now at Purdue. This is my lab when I was kind of fully packed in. A lot of them have graduated. I am in the rebuilding process now, recruiting students. And so broadly speaking, what is my lab about? I have this nice paragraph. It's looking at end users of products and systems. I also look at the designer or engineer in the process. But what I like to say is, my lab, we like to study and address interesting human-centered problems that matter. That, period. That's just bottom line. If it's interesting and it's human-centered, we might be interested. Broadly speaking, this is my research program, Daring to Be Different, Part 2, in mechanical engineering. This is the name of all of my little thrust areas here. As you can see, I love acronyms. I find ways to make acronyms out of everything. And so I have these 3 areas. I did not start out knowing that's what these would be called. I started to do research, and then I figured out how to cluster them in a way that was systematic. And these are examples of some of the projects that I kind of put in these categories. Some sit at the intersection, some sit purely in the main section, as can be seen. And so I want to talk about one that I call the beauty of mechanical engineering. It was funded by Procter & Gamble for 2 years, and the seed of the idea started in ME 555 when I started asking the question, how can we optimize hair care, particularly curly hair, women of color, because I'm a woman of color and I have that type of hair, and engineers can think about this type of thing. And so I couldn't do it as a dissertation topic. It just wasn't a good fit. So when I started my own lab, I was like, I could do what I want now. And so some of the motivation, a lot of women who used to use chemical relaxers, if you're not familiar with what that is, it's when you put a chemical that will permanently straighten your hair. And a lot of women stopped doing it because they found it's not healthy. So wear your hair the way it grows out of your head. So that's naturally curly hair. This is just a example of maybe not this as curly as it could be, but straight and curly. But one of the issues with people when they go natural and start using flat irons is if you use too much heat, your hair actually can still become permanently straight. And that's a picture here. You can see that she still has waves, but then the ends are just very straight from probably too much heat, and they call that heat damage. So the question that became a new curiosity at Purdue is what temperature and frequency of use would lead to these permanent structural changes in the curly hair. And so I'm like, okay, here I am in ME. Mechanical engineers, we know about heat transfer. We get that kind of training, but I didn't have a lab to do that. And so I collaborate with Amy Martinet who has the nanoscale thermal heat transfer laboratory. And we started to look at this problem. And I gave the project to a master's student. So this was me kind of tiptoeing, well, let me just give it to a master's student, just see what he can do with this. And again, just that daring to be different, because we're talking about hair in a ME department, and it's sort of, people can't wrap their mind around it sometimes. But now they can, because when you bring in money and you can publish papers, then they can wrap their minds around it. And when you get press, so that helps. Oops, did I go backwards? Okay, so some of the general challenges with that, people are using trial and error to figure out this problem. End users, they do not have the training to do it. So they're trying to help each other on YouTube. They have all these tutorials on how to avoid heat damage, how to, still use it and be safe with it. And then a lot of the styling tools that exist are not well understood. For example, before that, this is some of the ways women try to avoid using heat. Just like, okay, let me wrap my hair, let me use this threading method, let me do this banding to kind of straighten it, but without using heat. But if you look at these thermal tools like flat irons, we won't say who the manufacturers are. you can see all these inconsistencies on hair typing and temperature. And thin, fragile hair on one type, you could use 300 to 350 degrees, and then another one you could use 200 to 225. And then they have notes that talk about just the typical UL warnings. They don't say anything about heat damage, the risk of heat damage, probably because they don't know about it. And so some of the research questions that motivated this project are as follows. How does heat behave in different hair types? And so to do that, it involves thermal characterization of hair and heat transfer modeling of hair bundles with some experimental validation. And then the second question was, what is the impact of relevant flat ironing parameters on heat damage? And what we mean by flat iron parameters is not just the temperature, but how fast are you gliding over the strand of hair? Clamping force, frequency of use. Are you doing this twice a week or 3 times a week, or et cetera? And so this question was explored with an automated flat ironing mechanism. And so there are 3 small projects to answer this broader question, and so the purpose is described here. But the overall goal is to have a prediction of heat damage using this heat transfer model. So I won't go into a whole lot of detail with this, but this seed of an idea started in ME 555, and it has blossomed into this huge project that has allowed us to answer these questions. I will show you some key components of it. Jasik Khan is the graduate student that's working on it, and this is Amy Martinet, who has the nanoscale thermal conduction lab. This is the existing literature, how rare it is to find anything on human hair, particularly the thermal diffusivity details. Let me just jump to some slides I want to show you that I think would be very interesting to see. Okay. So one of the things that we were able to do is create a simulation of how the temperature changes as a flat iron glides over a strand of hair. So we have this model, the flat iron gliding over some hair, moves over the hair, and you can do an energy balance looking at heat from the flat iron through conduction and energy stored, and then convection to the environment. And in the simulation, you can track the flat iron temperature, the air temperature, and the position of the flat iron. And you can do this, you can see how it moves over time. And the goal is to see how long does hair stay above a critical temperature. And we set that critical temperature to 100 degrees Celsius. How long does it stay above that critical temperature? And the goal is to see, will that lead to heat damage? So so here is one pass. So this is just taking a flat iron and gliding it over a strand of hair at 1 centimeter per second at that temperature. And you can see the simulation of how the temperature profile of that hair strand over time, after you just do that one glide, how long the hair stays heated up. And similarly, for looking at 5 passes, going more quickly, so it's like 1, 2, 3, 4, 5, very quickly. How does the temperature profile change in the hair strand? Okay. So this is all simulation, and then the next thing is to conduct an actual experiment to see does it match the model. All right, so looking at exposure time versus position, this is generally how long the position of the flat iron and then the total time it stayed above 100 degrees Celsius, given, this is a typo here, given 1 pass versus 5 passes. And so an experiment was done. This is the flat iron mechanism here. We have an IR camera where we can see the flat iron mechanism. You could see how how the heat is on the flat iron as well as the hair. Okay. All right. And so here's a comparison between the simulation and the experiment with the same conditions. So it's not quite, it's similar, but not exact. And one of the reasons is because there's some other aspects to how the heat is moving from the flat iron that's not captured in the simulation. So this is just one of the projects. I think I'm going a little too deep on this one, but let's just move down to something interesting that came out, and then I'll move on to some other ideas. So after doing some studies, we came out with some suggestions on flat iron usage. So if women are focused on the strength of their hair, then you need to minimize or avoid the use of heat. And so this is so there's these three things that are playing, that have these trade-offs. It's hair strength, curl retention, and styling efficacy as defined by your ability to straighten your hair. So if you want to have strength in your hair, you cannot use heat. Do not try to straighten it too much. If you're curl focused, then you want to use flat iron at a lower temperature, but you can still have some straightening, but not a lot. If you want to be more balanced, then you can use a flat iron at a moderate temperature or a flat iron at a low temperature, so you could kind of be balanced. Or if you don't care and you just don't want to, you're not worried about heat damage, just go ahead, use it at high temperature, and you probably won't have much strength in your hair. You probably won't have any curls left, but go ahead and go at it. So that's kind of what we learned from some of our studies there. All right, I'm going to jump back from the hair project. We're going to move on. Okay. All right. Any questions about this before I move on to the next project? Okay. So, the next one is trust in human-machine interfaces. And this project, again, this idea of daring to be different, I went and purchased EEG equipment, skin conductance, device, eye tracking, because I wanted to know more about end users of products. And it turns out that I'm not just looking at end users, I'm looking at more than that. And this is how lots of collaborations actually on this side came about, because I had these tools. And the most interesting is this trust in human-machine interfaces project, which has opened lots of doors. The team here is no longer a grad student. She's Dr. Wanlin, Kumar Akash, and Neera Jain. And our goal is to understand this dynamic relationship between machine user interfaces and human trust in automated systems. The goal is to get an emotional intelligence algorithm for the machine to respond to the human in real time. And so the analogy is using a closed-loop feedback system. And if you're familiar, a closed-loop feedback system has your controller, an actuator, plant, and a sensor, and that you have a desired output you want to. So think about cruise control. You set your car to 60 miles per hour, and if you go down a hill, it's going to slow down, or if you go up a hill, it's going to speed up through the actuator. And in like manner, we created this trust model, and similar to the actuator is this user interface that would adjust according to what's going on in the mind of the person, and we will use sensors such as eye tracking, skin conductance, and EEG to capture what's going on, and this algorithm would help to control what's getting fed back to the human. And so the first part of this project is looking at modeling the trust in human-machine interfaces. Like, how do you come up with a generalized model to do that? And so we conducted an experiment, and this is the broad interface, and a person will see the obstacle detected. That's what they'll see as a stimulus. They're told that it's an algorithm that's being beta tested, and it's going to help them detect obstacles. And once they get some feedback on what the outcome is, they have to determine whether or not they trust or distrust it. And then they get feedback, whether or not they're correct. And so we had faulty and reliable trials set up, where the faulty trials would be 50%. There would be 50% of the time it's going to tell the person wrong when they're right. Where the reliable trials, it's always, whatever they said, it's correct. And so it builds this trust. And we created this 3-state human trust model that it accounts for cumulative trust and how bias affects that, as well as what we call a trust discounting factor, meaning as trust changes over time, like how is it adjusting? And here is an example of result based on actual feedback and the model. So the white, it shows up as white. The white is when it's reliable, and the gray is when it's faulty. And so we had it where sometimes they started out reliable, and another group started out where it was faulty. And as you can see, when it starts out with a reliable system, the trust levels go up, and then when it becomes faulty, it drops down, etc. But when it starts out faulty, the rise in trust is a lot slower in comparison to how quick the trust dropped when it transitioned from reliable to faulty. And then we looked at something called national culture, which is, there's a factor out there for United States citizens and Indian citizens, and then we split that to see how does it differ between cultures. And again, when you had different groups, if they started out with a reliable trial versus a faulty trial, you could see how it differed. And so you could see that United States citizens, if you compare the two here, the trust levels are pretty similar, but when it's faulty, it's a little bit less, like the recovery for US citizens is a lot less than Indian citizens. So a little bit more trustworthy on the India side than the US side. And a similar thing that you see when you start out with a faulty system. And then we looked at gender as well. And so we looked at this, and we found that there is a way to have this generalized trust model. And how do we then go beyond and look at the sensing itself? And so real-time sensing, how do we do that? And there's a gap where most of the automation, trust and automation work was not looking at psychophysiological measurements. So the prior study was just based on self-report. Now we're bringing in psychophysiological tools. So this is the overall framework of the study. We have the EEG measurements, GSR, and then we have the response behavior, like the behavior time. And we have these different, we have the data that we're extracting from each of these tools, and then how we extract out features to then figure out, okay, is this a trust response or is this a low trust response? And here's the setup. This is the Be Alert headset that we use in my lab, the computer-based simulation, and the skin conductance device. And what we have are the different measurements, and then there's an exhaustive set of potential variables that are extracted, and then a significant feature set is identified statistically. And here's the list of features that were identified and the source of the measurement, and then whether it's a time or frequency domain measurement. And so classifier training is done where you have this feature set, and then using these different models, whether it's SVM or QDA, it can extract out and cast a vote whether or not this is a trustworthy response or a low trust response. And here's an example of one person in what we call database one. This is the reliable set of trials, and then faulty is gray. This particular person, you see the trust levels are high, and then the trust levels are low according to this model. And person number 2, it's kind of choppy, it's down, it's up, it's down. And then person 3 is the worst one. So it's not, the model did not fit well for person 3. But for some people it fit really well based on their outcomes. And so this is helping us to see how accurate are these classifiers, and whether you used QDA or SVM, you can see that in general, it's about 71% accurate. but for some, the highest accuracy was 97, the lowest was 42. So from this particular study, again, using the EEG and GSR data along with behavioral data, we could see that we can extract out trust from individuals and create a generalized model using skin conductance and EEG. And so it's a first step towards real-time sensing of trust. Okay, the last thing I'll talk about that kind of fits in this realm of doing something different is compassionate design. So first time I attempted to apply for NSF career, I wanted to do it on this topic of compassionate design. And a colleague of mine said, wow, you're actually wanting to do something you care about. And I said, well, I mean, if I'm going to write 15 pages, I might as well do it on something I care about. Didn't get it that first time, but I got it not as career, but as another type of proposal through NSF. And the motivation for it, and this is the team that I worked with, this is my grad student and then a collaborator, is when I went to IU Hospital and saw individuals that were in the oncology unit and looked at how the radiation masks were created. It's like, okay, I mean, I know why they made it that way, but is this the best way to make something for a human? And then I met with someone who counsels breast cancer survivors and how they talked about the machine being this thing that they were afraid of, and it's the machine as an antagonist. And I said, how could we sensitize designers and engineers to think about these things in the design process? And so compassionate design is what that is. And it's not like empathic design, but it specifically focuses on the dignity, the empowerment, and the sense of security that end users feel when they interact with what you've created. And so this process started with looking at case studies of those that are doing it in a exemplary way and extracting out these key terms. So dignity and empowerment came from a Japur Foot case study, for example. Sense of security, the GE fMRI, I don't know if you're familiar with that, but how they created an experience around fMRI for children. And Lemon Tree Hotels, they empower employees to, no matter what they are like, whether they're physically challenged or have any learning disabilities, they are able to be employed and treated with the same dignity and respect as people without that. So looking at these case studies, we extracted these terms and broadly came up with, let me just go, this framework for compassionate design, and then created these design probes that can be used in the design process to help students or novices or any designers think about what they're doing. And so this is the first pass at some probes that we came up with that students have tried to use in their evaluation of their design. So you created this great thing, but will someone feel proud of it when they use it? Will they be embarrassed in front of people using it? Do they feel scared using it? So just kind of getting students and novices to think about this is the premise behind this particular project. And I'm going to wrap this up because I feel myself talking a lot. Design science, for the big thing to recognize is what is success in the organization that you're going to. For me, it's publish papers, it's raise money, teach well, graduate students. And then understand the fundamental skill sets that you will acquire as a result of your degree. My PhD was on looking at car shapes and measuring and quantifying their green perception and then putting it in an optimization framework that looked at fuel economy changes. Okay, as you can see, everything I presented had zero to do with any of that. Do you see any links between what I did as a PhD and with what I'm doing now? None. The only link is that there's humans and there's some psychology and thinking in the projects. And there's human subject studies in some of the projects and some tacit knowledge in there too. But I just wanted to stop here and end with this and take any questions that you may have.